Hello students, welcome to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So yes, you know we are doing a series where we are going to cover every concept of chemistry. We are going to practice a lot of MCQs, previous year questions, as well as we are also going to do test series, right? So this will be a holistic preparation for your KCET 2025 series examination so that you can get that perfect 60 score, okay? So in today's video, we are going to do coordination chemistry part 2. That is one of the most important chapter, most important segment also we are going to discuss today. That is nomenclature and isomerism. Okay, so I'll tell you this is not only important but it is also very interesting. Okay, we'll feel happy, we'll feel enjoying when we are doing these questions. I can guarantee you that. Okay, so yes, now I'll have one more request. Please join our WhatsApp channel. The WhatsApp channel link will be there in the description section, so you can go there and download it. Now, why is this important? That is, if you want the notes of these classes or any question papers, solutions, whatever we are providing, that will be available in our WhatsApp channel. Okay, so please join our WhatsApp channel. Do not forget to join our WhatsApp channel. This will help you to get all these materials, study materials. Okay, so yes, now I want all of you to sit with a notebook and a pen, and then you need to note down whatever important things we are going to discuss, and you have to resolve each and every question that I am going to do in this session. Okay, so question practice is very, very important for our KCET examination. Okay, so now without any delay, let's get started. Okay, so first of all, I'll tell you how am I going to cover this chapter. So I have already discussed in the part 1, but every time I want to remind you, so that when you are revising this chapter, you can see, okay, today I want to revise part 1, these two topics I have to revise, part 2 I'll revising these two topics, so it will be very much structured. Okay, so that is why I have divided it. So part 1, we have already completed Werner's theory and important definitions in our last class. Part 2, that is today's class, we are going to discuss nomenclature and isomerism. Okay, very interesting as well as important topic. Okay, next coming to part 3. So in part 3, we are going to discuss bond theories. That is your valence bond theory and molecular orbital theory, valence bond theory and crystal fault theory. And in part 4, we'll discuss metal carbonyls and application. So this will be a very short part. Okay, we'll be doing it just the important questions we'll pick up and we'll practice here. Okay, so yes, now today's topic, very, very important lecture. Okay, now weightage, as I already discussed, 2 to 3 questions every year you can expect from this chapter, and this chapter is highly important chapter, and its utilization is so much in the whatever researches are going on, everything is around coordination compounds. Okay, so that is why this is a very important branch of chemistry. Okay, fine. Now coming to what are we going to discuss today, as I told you, nomenclature and isomerism. In isomerism, we are going to discuss again stereoisomerism and structural isomerism. Okay, fine. Now let us start with nomenclature. Very interesting, very, very interesting. I'll tell you, it will be so interesting that you will be happy to solve questions here. Okay, so first of all, we will know certain rules of nomenclature. Okay, how to do nomenclature. Then once we have mastered these rules, then we will be solving all questions fatafat. Okay, fine. So the first rule is, there will be two parts in a compound. One is cation and one is anion. So the first rule is that the cation should be named first in both the positively and negatively charged coordination entities. So whatever it is there, suppose you have two coordination entities, the cation should be named first and then anion. Okay, first cation, then anion. Got it? Second rule is, so the rules you may not understand all the rules now, but when we are applying it, I'll explain each and every rules. It will be very, very clear. I can guarantee you. Please understand the rules with me now. Now first, the ligands are named in the alphabetical order before the name of the central atom. So now if you see in one coordination pair, what is there? Metals are there and then ligands are there, right? So the rule says that first we should name the ligands, and if there is more than one ligand, the ligand should be named in alphabetical order. Okay, so after naming the ligands, we need to name the metals. Okay, third rule. Now, names of the anionic ligand end in O. Okay, anionic ligands means if the ligands are negatively charged. For example, chlorine. Chlorine name with end with chlorido. Chlorido. This O is there. Okay. For example, CO3 2-, carbonato. Okay, so I'll tell you the ligand names also, do not worry for that. And those for the neutral and cationic ligands. Ligands are very rarely cationic, but some ligands are there, exception. But still, neutral ligands are named except aqua for H2O, amine for NH3, carbonyl for CO, and nitrosyl for NO. So the cationic ligands are named as it is, okay, but certain ligands like neutral ligands for water, we have given a name aqua, for NH3 amine, carbonyl it is CO, and nitrosyl it is NO. Okay, so you have to remember these names. Okay, that I'll give you a list. Now you might be thinking, ma'am, what is how many ligands are there, how many will remember? So we will be practicing so many questions. The most used ligands, I'll give you the list, their names and the charge. Okay, fine. Next. Okay, now prefixes like mono, di, tri, etc. are used to indicate the number of individual ligands in the coordination entity. Now suppose there is 2 chlorines are there, we'll use dichlorido. Okay, dichlorido. Now when the name of the ligands include a numerical prefix, then the terms bis, tris, tetrakis are used, the ligand to which they refer being placed in the parenthesis. Okay. So now suppose there is some numbers in the ligand itself, like for example you can say ethane 1,2-diamine. This is ethane 1,2-diamine. Okay, such type of ligands where there is number in the name itself. For them we will not use bi, tri like that. For them, for 2 we need to use bis, for 3 we need to use tris, and for 4 we need to use tetrakis. Okay. Next, after that, oxidation state of the metal in cation, anion or neutral coordination entity is indicated with Roman numeral in parenthesis. Okay, so the metal oxidation state has to be given in the Roman numbers and it should be in the brackets. Okay, next, last one, if the complex ion is a cation, the metal is named same as the element, but if the complex ion is an anion, the name of the metal ends with suffix ate. Okay, so now what I am saying here, see. Okay, so now we will understand the structure in detail, then we'll do example. So how the name should look? First, your name should contain cation part, okay, and then the name should contain anion part. Okay, so case 1 I am telling where the complex is cation, okay, and this one anion is there. It is not a complex. Okay, so in this case how will you name? First the ligand name should be there. Okay, ligands names, all ligands in the alphabetical order, by, try you will use and write the ligand, then we'll write the metal name, and then we will write the oxidation state of the metal, right? Now case 2 is what? That cation is there and the complex part is anion. Once example is there, it will be clear, but still I am telling here now. Cation is there and the anion, the complex is the anion. Now how the name will be there? First cation and then anion. So here there will be the name of the cation. Okay, here in the anion name, first the ligand's name will be there, right? Then metal's name will be there. Now if this metal is a part of the negative ion or the anion, then the metal name should be ending with ate. That is what is the last rule saying you. And then the oxidation state in Roman numbers. Okay, so now I think many of you might be confused, might have did not understand anything. It may happen, but once we will start solving 6 to 7 examples, it will be very clear. Okay, we'll start solving examples. Before that, here is the list that you need to remember. Different ligands are there. Okay, I'll tell you the most important ligands and you need to remember their charges also. So F minus, Cl minus, Br minus, I minus. What are their name? Fluorido, chlorido, bromido, iodido. SO4 2 minus, sulfato, OH minus, hydroxo, Cn minus, cyanido, C2O4 2 minus, oxalato, CO3 2 minus, carbonato, CH3CO minus, acetato, O2 minus, oxo, O2 2 minus, peroxo, O2 minus, superoxo. So these 3 are not generally asked in the exam. Now here from Cationic ligands, you can remember NO plus and NO2 plus, okay. Nitrosonium and nitronium, these are not asked in the exams, but still just have a look at it. It may be asked, but generally these two will work. Coming to neutral ligands, NH3 is amine, H2O is aqua, CO is carbonyl, NO is nitrosyl, O2 is dioxygen, N2 is dinitrogen, C5H5 is pyridine, and then this one is ethylene diamine. Okay. Ready students, let's go and solve the questions now. I hope all of you may not have remembered the rules, but do not worry, we'll apply the rules here. Now coming to the first one. Okay, so now you see this is a metal. Okay, these are the ligands. So what are the ligands written here? There is one ligand NH3, okay, there is chlorine and there is NO2. Okay, so these are the ligands. So what is the name to be used for NH3? That is amine, right? For chlorine we have to use chlorido, okay. And if you see NO2, what is used? NO2 I haven't given, okay, let me add it here. NO2 is nitrito N, okay. If it is ONO, then it is nitrito O, okay. So I'll arrange here nitrito N, okay, fine. Okay, now this I'll write nitrito N. Okay, now if you see alphabetical order, first this one will come, then A, C and then N, right? Okay, so first of all we should write the ligand's name, then metal name, then the oxidation state. What is the step? Ligand name, then metal name and then the oxidation state. So first let us calculate the oxidation state of metal. Okay, so now you see NH3 is a neutral ligand. So first calculation of oxidation state, I'll take PT, oxidation state is X, NH3 is 0. There are chlorine, so chlorine is -1, NO2 is also -1, ligand NO2 is also -1. So what I'll get? X is equal to +2. So platinum charges, oxidation state is +2. Okay. Now we are ready to write the name of the compound. So NH3 is there, 2 NH3 is there, so we have to write diamine. Okay, diamine. Next chlorido. Next nitrito N. Okay, next what is the metal? Platinum. So is it a anionic complex? No, it is a neutral complex. So the name of the metal will be as it is, that is platinum. Then in the bracket what I need to write? The oxidation state, that is 2 in the Roman numbers. Clear? So we need to write it in the Roman number. So this is the answer for this particular example. Now let us go for the next one. So what is here? You see, this part is cation and this part is anion. This is cation, this is anion, right? Okay. So first of all, we need to calculate the oxidation state of metal. Okay, let us do. Potassium is +1, there is 3, so I can write it 3 here, plus. Chromium I need to find out, so let it be X. Okay. Then C2O4 is oxalato, right? C2O4, if you see oxalato, the charge is -2 here, so you have to remember the charges also. So -2, how many oxalato are there? 3. So 3 into -2 will be -6, that is equal to 0. So here what is the value of X? +3, right? So chromium oxidation state is +3. Now one more thing you should remember, I have already discussed that this is called counter ion, right? The one which is present outside the parenthesis or outside the square brackets are called as counter ions. So for counter ions you need not write tripotassium, not like that. Only you have to name the write the name of the elements. So what is the element here? Okay, first let us discuss about the ligands. What are the ligands? Only one ligand is there, oxalato is there. Okay, so now we'll write potassium, cation. First rule, what does it say? Cation should be named first. So I have named the cation. Now anion I have to name, right? In the anion, ligands should be named first. So how many? This ligand name is oxalato. How many ligands are there? 3. So I will write trioxalato, right? Then I have to write the metal name, chromium. Okay, now you see, I told you that if the metal is a part of the ligand, if the metal is a part of the anionic complex, then its name should be ending with ATE. So here metal is a part of the anionic complex, the metal is a part of the anionic complex, its name should end with ATE. So what I'll get? Chromate. Okay, what's the oxidation state? 3. So potassium trioxalatochromate 3. Then, okay. Next one. Let us try the next question. So if you say this one is your cation, this part is anion. So we have to name first this one. First let us calculate the oxidation state of the metal. So cobalt, let it be X. Okay. Cl2, each chlorine is minus, so it is -2. En is a neutral ligand, so +0. And then here it is -1. I'll get 0. Neutral compound, so 0. What's the oxidation state of cobalt here? +3. Okay. So now we will solve it. In the cationic part, I have to, what are the ligands I have? See, one is chlorine, so I'll write chlorido. Okay, another ligand is ethane 1,2-diamine, so it is called as ethylene diamine. Okay, so you can see the name here if you have doubt here, ethylene diamine. Okay, single M is there, ethylene diamine, 1 M only. Okay, sorry. Right, we got this one, ethylene diamine. Now what we can do? Now see, I told you for this particular, this is also ethane 1,2-diamine, it is written in its name, there is number. So for this one, if it is 2, we cannot use bi here, we need to use bis here, right? Now if you say letter wise, which one will come first? Alphabetical order, this one will come, then this one will come, right? So first, let us write now. First the ligand's name I'll write, so there is dichlorido. Then this part is done. Then this one is bis ethylene diamine. Okay. Next I have cobalt. Okay. Now oxidation state of cobalt is 3, so I wrote 3 here. Now as I told you that this is a part of a cationic complex, metal is a part of the cationic complex, so here the name will not end with ATE. Right? If the metal is a part of the anionic complex, then the name ends with ATE. Right? So this is done here. Now coming to chlorine. So chlorine we have to write, because it is a negative ion, it will be chloride. Okay? So from this way we can get the name of this particular compound. Now let us write example for this one. Now if you see again here, right, this is what? Cation and this is anion. Okay? So here what are the ligands present? First let us calculate the oxidation state. Let cobalt oxidation state is X, NH3 neutral ligand, so 0. Carbonate is 2-. Okay, so you can see the charge here, carbonate is 2-, right, CO3 2-. So this is 2-. Then chlorine is again -1 is equal to 0, so X is equal to +3, right? Okay, now if I write here, 1 second, okay, now this is what? Cationic part. So what are the ligands list are there? First is your amine. Okay, 1 second, we have NH3 as AA-M. Okay, so amine ligand is there, and then we have carbonato. Okay, so if you see here, for CO3 2-, the name is carbonato. Okay, so now let us try this one. Okay, now you see, first alphabetical order, this one will come, then this one will come, right? So first we'll write amine. How many amines are there? 5 amines are there. So I can write pentaamine. 1 second. So yes, we can write pentaamine. Okay, then we have carbonato. Then we have cobalt. Okay, in cobalt the oxidation state is +3. Okay, cobalt +3, then chloride. Okay, so if I just erase it, okay, so this is pentaamine carbonato cobalt 3 chloride. Okay, that is the name of this particular compound. Okay, now let us do some more question here. Okay, so here now if you see, Okay, this is cation, this is anion, right? The complex is now anionic part. So what is the rule you have to remember? Metal name should end with ATE. Okay. So now coming to calculation of oxidation state of this one. So mercury +1, okay, cobalt we need to find out, okay, SCN charge is -4, okay, sorry, -1, each SCN is -1, so charge is plus, like 4 SCN is there, so -4, that is equal to 0, so X is giving you +3. Okay, now what is the name of SCN? So I think this is also not there, we will add here. In the list I am adding whatever is not there. So for SCN, okay, we have to use thiocyanate S. Okay, if it is NCS, then we have to use thiocyanate N. Okay, fine. Now let us move towards this. And okay, so first is what are the ligands here? Only one ligand is there. Okay, so we have to first write mercury, then that is how many is there? Tetra, thiocyanate, okay, tetra thiocyanate, S or N? This is S, right? So we have written, then we'll write the name of the metal, cobalt. Okay, but now again you have to remember metal is a part of the anionic part, so name will end with ATE. So cobaltate 3. Then okay, now let us see the next example, AgNH3 whole 2 AgCN2. Okay, so now you see this is a cation, this is the anion. Okay, so cation and anion has combined means they will not be neutral. There is one cation and one anion, so there will be some charge between them. So this will be +1, this will be -1. Okay, so now if you see in this one, silver charge is +1 here. Okay, if you calculate here, silver charge is, if I see here, this is X, okay, this is X, 2 negative Cn is there, so -2 is equal to -1. So what I can say, X is equal to +1. So here also silver is +1. Okay, so now what I can do, I'll write the cationic part first. So there is a ligand amine and there is 2 ligands. So I'll write diamine. Okay, silver, oxidation state is 1, Roman number. Then I'll write the anionic part. Here it is dicyanedo or cyaneto, you can write anything. Cyanedo is also correct, cyaneto is correct. Then, but here the metal is a part of what? Anionic complex, right? So we have to end the name of the word of the metal with ATE. Now we'll not use silver, we'll use its original name, that is argentum. So what will happen? The name will become here argentate, and again the oxidation state is +1. Okay, so yes, these are some of the examples that we have practiced. We'll be doing more also. Now let us do some opposite way, that is where the ligands names are given, the name of the complex is given to you, and you have to make its, you have to draw the structure. Okay, so now let us first write tetraamine, okay, aqua, chlorido, cobalt 3 chloride. Okay, so this part is your complex and this part is your what I can say is your anionic part. Okay, so now if I see tetraamine, so what is the metal? While writing, metal should come first. Cobalt is the metal, tetraamine, so there is 4 amine. Okay, aqua, there is 1 H2O. Okay, chlorido, there is 1 chlorido, right? This is there, and then cobalt chloride is there. But how many chlorines will there, that we need to figure out. So how we can do? We need to calculate the charge of this complex. How to calculate the charge of the complex? See, cobalt is 3, okay, this is 0, water is 0, and there is 1 chlorine, 3 minus 1. So I can say that this is +2. The total charge of the compound is +2 and chlorine, as you know, is -1. So what happened? Now they will do crisscross, right? There will be a crisscross of the ions. So I can get now the formula as this +2 is there, this is -1, this will come here, this one will come here. So I'll get CONH3 whole 4 H2O Cl, then Cl2. Right? So now if you check, how can you cross check? You can just cross check here that cobalt charge is X, let us make it X, this is 0, this is 0, this is -1, this is -2, will get 0, so X is equal to +3. Okay, so like this you can cross check. Okay, so the final answer, this one you should be very careful what should be the number here. Now coming to next one, potassium. Okay, first is potassium, then this part is your complex. Okay, tetrahydroxidozincate, that means zinc is there, tetrahydroxido means 4 OH is there. Okay, and zinc charge is 2. So we'll K we know is +1, right? Now we'll calculate the charge of this complex. How can we do that? Zinc charge is 2 here. I'll write zinc charge is 2, and there is 4 hydroxide ion is there. Each is -1, so there is -4. That is equal to, I can say, -2. So this is -2. So now there is a crisscross happening. This one, this is crisscross of the valencies. This 2 will come here. This one will go here. So finally, what I'll get? K2ZnOH whole 4. K2ZnOH whole 4. Getting? Okay. Now let us do the next one. Potassium trioxalatoaluminate 3. Okay. Now if you see first, this is potassium is cation and this part is your complex, right? So potassium, done. Trioxalatoaluminate 3. So that means what? In the complex we have aluminium. Trioxalato means we have C2O4. Okay, trioxalato C2O4. Trioxalato C2O4. Done. Now we are not done here. We need to calculate the charge of this negative complex. Potassium we know it is +1. Now if you see here, aluminium is in +3 state, right? And oxalato, each oxalato charge is -2. So 3 means -6. 3 into -2 is -6, and that is equal to -3. Okay. So now if I solve it, what I'll get? K3, okay, Al C2O4 whole 3. Clear? Getting? Now let us do the next one. So dichlorido bis ethane 1,2-diamine cobalt 3. Okay, so this is only a complex there is no cation anion. So dichlorido, first we'll write the metal name cobalt, dichlorido means Cl2, and then we have ethane 1,2-diamine is written as En. Okay, En, how many is there? Bis means it is 2. Okay, what will be the charge of the complex? Let us calculate. This is +3, right, and this is -2. Because each chlorine is -1, so 2 chlorines is there, so it is -2, and this is a neutral compound, right? So +3 I'll get +1. So the charge of the complex is +1. Okay. Next, coming to the fifth example here, tetracarbonyl nickel 0. So nickel is here 0, then tetracarbonyl means CO is 4. Okay. So if you see now, this is 0, this is also 0, so this is a neutral compound. Clear? Got it? Okay, fine. So we are done with the nomenclature and all. Now we'll go to the next part of our topic, that is isomerism. Okay, isomerism is also very easy and scoring, but you need to have a very clear idea of the classification of isomerism. Okay, so I'll be telling you how the isomerism is classified. So the first, isomerism is of 2 types, stereoisomerism and structural isomerism. Okay, let us repeat. Isomerism is of 2 types, stereoisomerism and structural isomerism. Okay. Now coming to stereoisomerism. Stereoisomerism is of again 2 types, geometrical and optical. Getting? Let us repeat from the starting. Isomerism is of 2 types, stereoisomerism, structural isomerism. Stereoisomerism is again of 2 types, geometrical isomerism, optical isomerism. Let us repeat. There is isomerism, 2 types, stereoisomerism, structural isomerism. Stereoisomerism is of 2 types, geometrical and optical. Okay. Now coming to structural isomerism, that is of 4 types, linkage, coordination, solvation and ionization. Okay. So that are the 4 types of structural isomerism: linkage, coordination, solvation, ionization. Okay. Let us repeat from the starting. Ionization is there, 2 types of ionization, isomerism is there, two types of isomerism, stereoisomerism, structural isomerism. Stereoisomerism is of two types, geometrical and optical. The structural isomerism is of four types, linkage, coordination, solvation, ionization. Okay. Now coming to geometrical isomerism, now coming to geometrical isomerism, we are going to study for two things, that is when the coordination number is 4, when the coordination number is 6. Okay. Now when the coordination number is 4, okay, if the coordination number is 4, there is a complex can be either square planar or it can be either tetrahedral. Okay. So what happens, square planar can show you cis and trans geometry, okay, but tetrahedral does not show geometrical isomerism. Clear? In coordination number 6, we have again three combinations, like three possibilities are there. MA4B2 type, here again cis and trans is there. MA2LL2, here also cis and trans is there, and here MA3B3. We'll be explaining each of this. Okay. Now let me revise everything together. Isomerism is of two types, stereoisomerism, structural isomerism. Stereoisomerism is again of two types, that is your geometrical isomerism and optical isomerism. Okay. Now geometrical isomerism, we are going to, so this is not the type of geometrical isomerism, I am telling what we are going to study. Under geometrical isomerism, we have two things, coordination number 4 and coordination number 6. Coordination number 4, if it is there, the shape of the or the geometry of the molecule is generally tetrahedral or square planar. So in tetrahedral there will be no geometrical isomerism, but in square planar it can be cis or trans. Now coming to coordination number 6, if coordination number 6 is there, if we have a ligand of MA4B2 type or MA2LL2 type or MA3B3 type, then we can see geometrical isomerism here. Coming to structural isomerism, we have four types, linkage, coordination, solvation, ionization. I hope this flowchart is very clear. I want all of you to draw it, keep it and understand this. Okay. Now we'll first cover stereoisomerism. Okay. So under stereoisomerism, the first one I told you is geometrical isomerism, the other one is optical isomerism. Under geometrical isomerism, I told you coordination number 4 is there, coordination number 6 is there. Now for coordination number 4, there are two types of shape, that is square planar and that is tetrahedral. So if you want to know how the square planar looks, square planar is like this, A is there, then these are the ligands. Okay. So this is the structure of square planar. Now what is tetrahedral? A is there, okay, this is square planar, okay, and this is tetrahedral. Okay. Now what happens, in square planar we can find cis and trans geometry. Now for example, if you have this, you can see this example, PT NH3 whole to Cl2, PT NH3 whole to Cl2. So now if you see here, if the NH3s are on the same side, okay, then we call it cis isomers. If you see the NH3, okay, so this is what type of, this is MA2B2 type, okay, two ligands are of one type, two ligands are of the other type. So if the same type of ligands are on the same side, we call it cis. If the same type of ligands are on the opposite side, we call it trans. Okay. Now coming to tetrahedral, tetrahedral molecules does not show geometrical isomerism. Clear? So in coordination number 4, we have to study very little. MA2B2 type, two ligands on the same side of same type will give you cis, two ligands on the opposite side of the opposite type will give you trans. Okay, fine. So now see what we have completed now. I told you stereoisomerism. Stereoisomerism is of two types, geometrical and optical. In geometrical, there is coordination number 4 and coordination number 6. So coordination number 4 we have done. There in coordination number 4, two types of geometry is possible, square planar and tetrahedral. Square planar will show geometry cis and trans. Tetrahedral will not show any geometry. Now how to know cis and trans? If same type of ligands are on the same side, we call it cis. If the same types of ligand are on the opposite side, we call it trans. Okay, that is clear. Now coming to this one. Here this is coordination number 6, means 6 type of bond metals will form 6 bonds. Okay. So now if you see MX4L2, okay, so here what happens, see, if I draw MX4L2, see, now this example if you can see here is cobalt NH3 whole 4 Cl2, cobalt NH3 whole 4 Cl2. So there is one ligand, that is 4 ligands of one type, and 2 ligands chlorine is present. Now if this Cl2, the 2Cl is present on the opposite side and the 4 NH3 are present on one of the plane, then this is called as trans. Okay. Now if the chlorine, if this, apart from this you do any other geometry apart from this will be called as cis. Okay. So you can see here 2 chlorines are not opposite here, you can put chlorine here, not except here, you can put anywhere. So I am telling you, except this geometry, whatever you draw, that will be counted as cis. Okay. So now in MX4L2, if the two ligands which are 2 in number, if they are on the axial position opposite to each other, that is called trans. Apart from that, whatever positioning you do, that will be called as cis. Okay, this is one example of 6. You can see we have 2 NH3 and 3 NH3 and 1 chlorine in one plane, and chlorine and NH3 on the opposite plane. Okay, fine. Now coming to MX2LL2. Now what is this LL given in bracket? So that means it is a bidentate ligand. So in this case, how the molecule looks, see, we have M. So I have 6 bonds, right? In octahedral the geometry is like this. So this is done by 1, this is taken by 1, and here there is, I can write X and X. Okay, like this it will be existing. Now if you see the example here, okay, now the example here is CO Cl2 En2, CO Cl2 En2. Okay, now if you see this, what is there? Cobalt is present. Okay, now see, cobalt is present. Okay, and the 2 chlorines are on the same side, and this is one En, this is one En. So this is your cis geometry. Okay, cobalt is there, 2 chlorines are occupying. So if I draw the site here, see, 1, 2, 3, 4, 5, 6. Okay, so if the chlorines are present here adjacent to each other, okay, then whatever you will get En here, that is your cis geometry. Now in case of trans, what we are doing? Trans, we are taking 2 chlorines on the opposite side. So this is called trans geometry. 2 chlorines are present on the opposite side. This is En, this is En, right? That is called trans geometry. Okay. Now coming to MA3B3. So in MA3B3 type, also you can see coordination number is 6 because 6 bonds are formed. So here you understood why the coordination number is 6, because metal is forming 6 bonds, right? 1, 2, 3, 4, 5 and 6, right? Okay, now I will erase this one. Okay, now if you see here in MA3B3 type also, there is coordination number 6. But in MA3B3 we do not use the word cis and trans. We use something called as facial and meridional. Okay, so if you see here, okay, now see the example taken here is for CONH3 whole 3 and NO2 whole 2. Okay, so the compound taken here is CONH3 whole 3 NO2 whole 3. Okay, MA3B3. Now if you see that the 3 of the ligands are on one side. Okay, this is one face. Okay, you can see of the octahedral, this is a one face of octahedral. So you can just imagine if 3 NH3 on one side and 3 NO2 on one side, if such type of geometry is there, we call it FAC, okay, facial. And if this is not there, okay, there NO2 is present like this in this type of phase, okay, it is not a phase of this one octahedral, then we call it meridional. Okay, once again let us discuss this one. If 3 NH3 on one side, and you can imagine like this, this is octahedral, this is the position, right? If I draw how does the octahedral looks? So octahedral has 6 phases, right? 1, 2, 3, 4, 5, 6. So if I say that this 3 and this 3 are occupied by one type of ligand and this 3 is occupied by one type of ligand, we call it facial. If this is not there, any other configuration is there, we call it meridional. Okay, so the facial and meridional are isomers of CONH3 whole 3 NO2 whole 3. Okay, now questions are generally not much asked from here, but yes, this one is very, very important. Now coming to 4.1.2, that is our optical isomerism. Okay, so now optical isomerism means what? That the compound and its mirror image, compound and its mirror image, okay, are non-superimposable. Non-superimposable. Now what is it? Non-superimposable means, see, suppose you have a letter A, okay, mirror image of A will be like this. Now if I want to keep this A on this one, so it will exactly overlap, right? But suppose I have a letter B, okay, and I draw its mirror image. How will it look? It will look like this. If I take it and keep on this, will it be imposable? It will be exactly imposable? No, right? So if the mirror images are non-superimposable, then they show optical isomers. Okay, if the mirror images are non-superimposable, then they show optical isomers. Clear? Now we'll go back to our example. Okay. Okay. Now see here. Okay. Now first we'll take this example, that is, okay, the first one is of the type where we have MLL3, okay, means 3 bidentate ligands are there. You can see En, so this is like this, En, En and En. So if I draw its mirror image, it will look like this, right? Now this molecule is not superimposable on this one, right? If you impose this one, this En will be coming outside, right? It is not exactly superimposable. So I can say that this type of molecules where this, you remember, this type of formula, if it is there, then it will have optical isomerism. Okay. Now let us see this example. So if you see here, this is of type MX2LL2. Okay, so just now we discussed that it has two forms, cis and trans, right? So the cis form of this one can be optically active. So if you see here, this is the cis form, right? Now this is the cis form, ClCl is there and En are on the opposite side. If I draw its mirror image, I'll get this one, which is non-superimposable on this one, right? But now what is, ma'am, can you tell me about the trans one, whether trans one is optically active or not? So if I draw the trans of this form, then what I'll get? M, okay, I have X and X like this, okay, and then I have like this, okay. Now if I draw the mirror image of this one, I'll get X like this, again this is like this and this is like this, right? So this one is superimposable on this one. So that is why the type MX2LL2 type, remember, cis is optically active, okay, but trans of this type is optically inactive. Okay, here it is optically active and this one is optically inactive. Okay, fine. Let us do some questions now. Out of the two coordination entities, which is chiral or which is the meaning, which is having optically activity or optically active? So now just now I told you this is of type what? MX2LL2 type, right? MX2LL2 type. So in MX2LL2 type, I told you it can be of cis or it can be trans. Now you should remember that cis is optically active and trans is optically inactive. Optically inactive. Okay, getting? Now in this case, what, which will be chiral? Obviously cis one will be chiral, right? Correct answer is A. Now coming to next one, which of the following coordination entities will show geometrical isomerism? Means it can show cis and trans form. So if you see, this is MA3B3, okay, this is MA3B3 shows you facial and meridial, okay, we need cis and trans. So PTCl2NH3 whole 2, this is of the type MA2B2 square planar, right? Okay. Next, if you see PTClNH3 whole 5, so there are 5 ligands here, so there cannot be cis and trans here, and there is 6 ligands of the same type here, so this cannot be also your cis and trans. So the correct answer here will be option number B. Now let us draw and see them to be more clear. So if you see, platinum is there, okay, and we have chlorine and we have NH3, Okay, this is one form. Another is there platinum, we have chlorine, then we have NH3, and then we have NH3. Okay, so the correct answer for this question will be option number B. Now coming to next one, that is question number 5. Which of the following will exhibit optical isomerism? Okay, so optical isomerism, we saw which all are having optical isomerism. M, L, L, 3, this type, or M, X2, LL2 type, and this one cis form. Trans will not exist. So these two types of molecule will have optical isomerism. So if you see here, this one is H2O4, it doesn't matches here, so we can eliminate this one. Okay, next you see COEN3, this is of this type, right? This can be the answer, Here CONH3 whole 6, again this is not there. This is of this type, but this is trans, so this is also not there. The correct answer for this question will be option number B. Okay. Next question. Okay, so now let us go to the next topic, next type of isomerism, that is structural isomerism. This is very easy. So structural isomerism is of 4 types. First is your linkage isomerism, then we have coordinate isomerism, then we have ionization isomerism, and the next one is solvation isomerism, right? So now linkage isomerism means what? I have an example here and we will be discussing the answer of this one. Now see, linkage isomerism means I have told you something about discussing about ligands, that is ambidentate ligands. So now you see in this particular isomer, the NO2 is bonding with cobalt through N, but NO2 has also a ability to bond with O, right? So the linkage here is with nitrogen. If the same molecular formula I take, but I write like this, CO NH3 whole 5, okay, and then I write ONO, okay, Cl2. So now you see this is linking through N, this will link through O, right? So this is called as linkage isomerism. So for linkage isomerism, what I need? We need ambidentate ligands, okay, ambidentate ligands, getting? Okay. Now let us go to coordinate isomerism. So in coordinate isomerism, what happens? We have two like coordinate spheres. What we can do is we can exchange the metals here. Okay. So if I exchange the metal, what I'll get for this one? So I can write here, chromium will come here. So I'll get chromium NH3 whole 3, NH3 whole 6, and cobalt will come here. So I'll get CO CN6. Okay, when the two coordinate spheres are there, you can just exchange the metals, then we call it as coordinate isomerism. Next, coming to ionization isomerism. So you can see the example here. Now see, if you take this one, what ions will get? This coordinate sphere and then bromine ion will get, right? Just what ionization isomerism you can do, you can take bromine inside and sulfate outside, right? So when you ionize this one, we'll get this one and this one. So ionization isomers means we get different ions are produced. Different ions are produced when you put it in water, okay? Next, coming to solvation isomerism. So solvation, you can understood that it must contain water, okay? So you see here there are 5 water molecules and 1 more water molecule is outside. So what I can do is I can take this water molecule inside and I can take this chlorine outside, right? So these type of isomers where water, so this is very similar to your, you can say this one ionization isomerism, but it should have water molecule. So you can take water inside and can put another ions outside, okay? That is called solvation isomerism. Clear? So I hope these isomers are very clear. Now let us revise it once again. Linkage isomerism, very simple. If you find an ambidentate ligand, it will show linkage isomerism. Now coordinate isomerism is also very easy to identify. You need 2 coordinate spheres. One metal, you can just exchange the metals between them, will get coordinate isomers. Now coming to ionization isomers. In ionization isomers, what happens? You can, like, what ions are produced here, you can just shuffle between the ions, okay? Then we'll get ionization isomers. Solvation, you need to do the same thing, but you have to do with water molecules, okay? Fine. Now let us see the question. The pair of CrNH3 whole 5 NO3 SO4 and CrNH3 whole 5 SO4 NO3. So you see this one and this one has got exchanged here, right? So that is what type of isomers. So when you put it in water, we'll get this as an 1 ion and sulfate as 1 ion, and then this one as 1 ion and NO3 as 1 ion. So this type of isomers are called as ionization isomers, right? Okay, so now we will practice some questions, that is your PYQs, but before that we'll do the question that I gave you as a homework in my previous lecture. How many ions per molecule are produced in the solution when more salt is dissolved? So for that you need to know the formula of more salt, that is FeSO4 NH4 whole 2 SO4, right? So if I put it in this in water, so what I'll get? Fe, I'll get 1 ion, Fe will be produced 1, right? Sulfate, I'll get here 1 sulfate, here 1 sulfate, so 2, and then ammonium I'll get 2. So I'll write the charge. Okay, so how many ions total we are getting? 2 plus 2 plus 1, that is 5, right? So the answer for this question will be option number A. Okay, fine. Now let us do PYQ sum. Number of stereoisomers exhibited by this one. So if you see, this is your LL2 X2 type, right? MLL2 X2 type. So now if you remember, this one can have cis and trans, right? And the cis one will have its optically active form also, the mirror image of this one. So how many total stereoisomers we will get? 1, the cis one, trans one, and then optically active one, right? So if I draw this, we'll draw it also and check. So I'll do the cis one here, CO. So okay, so this is En, and we have Cl2, right? This is the cis form. Now if I draw the trans one, CO, Cl, then we have here En, and then we have here En, right? Now this is one geometry we got, this is the trans form. Okay, now the mirror image of cis is also isomer which is optically active. So it is asked, I can draw the mirror image of this one. We'll get En here, and then Cl and Cl. Okay, so if we solve this, we'll get 3 isomers. Okay, the correct answer for this question will be option number C. Okay, now coming to question number 2 here. FeNO2 FeONO shows. So as I told you, if there is an ambidentate ligand, undoubtedly blindly you can say that it is linkage isomerism. So correct answer is option number A. See how easy questions have been asked from here. Now next one, IUPAC name of this one. Okay, let us see. We'll eliminate the option. So first of all, we need to name this complex, right? In this complex, what are the ligands? Amine and carbonato. Amine, there are 5, so the name must start with amine because alphabetically order A comes first. So here there is pentaamine, it can be the answer. Carbonato we can eliminate. Here also pentaamine, here also pentaamine. Okay. Now after pentaamine, then another ligand should come. Carbonato name should come. So here it is carbonato, here it is carbonato, but here cobalt has come. So we can eliminate this option. Next, if you see, cobalt is a it is a part of the cationic complex, right? So the name should be as it is cobalt. Okay, but here you see it is cobaltate. It is like this one we have to use when cobalt is a part of the negative ions, right? Negative anion complex. So we can eliminate this option also. The correct answer for this question will be option number A. Okay, fine. Next, coming to question number 4, that is the formula is given and we have to find. So first of all, penta aqua is given. Here you can see 6 aqua, here also 6 aqua, so we can eliminate these 2 options. Next, penta aqua nitrato. Okay, nitrato means, again we have okay, nitrato is NO3. Nitrato is it is either like what, NO2 or ONO, but when it is told nitrato, okay, that is NO3. So we can eliminate this option also because it is nitrito. Okay, so we can eliminate. So the only option that is left with us is option number C. Okay, now okay, we will check this one also. The charge also we can calculate here. See whether the charge is coming +3 or not. So if you see, let it chromium be X, water is 0, right? This is minus 3 and this is minus 2, that is equal to 0. So x is equal to plus 3. Okay, the correct answer is option number C. Now coming to the last question, which of the following will be able to show geometrical isomerism? So we have seen tetrahedral molecules do not show geometrical isomerism, right? We can eliminate these two. Now square planar, which type will show? Either it has to be MA2B2, okay, or MABCD can show. I think I might not have mentioned this, but we have discussed about MA2B2 or MABCD. So MA3B will not show. The correct answer will be option number D here. Okay, fine. Now coming to a homework question. So please try this question. This is from your structural isomerism and geometrical isomerism. So just check all the options, think about them, and then you can answer. Okay. So students, that was the end of the most, I'll say, interesting, easy and scoreable part of the coordination chemistry, that is your isomerism and nomenclature. I hope you would have enjoyed and would have understood all the concepts. If you have any doubt in these concepts, do not forget to comment down. Your teacher is here to help you in every aspect. Okay. So yes, if you have enjoyed this series, if you are getting something benefit out of this series, and if you are really thinking it is helping you to score or to improve yourself in your chemistry, do not forget to subscribe the channel. And as I requested you, please join our WhatsApp channel so that you can get access to all these notes, questions and solutions. Okay. So yes, students, please remember, the only one thing that we have to remember is we have to hit that perfect 60 score in our KCET Chemistry 2025 examinations, and we have to work hard for that from today. So yes, do not forget it. Keep working hard, and see you soon in the next class with another important and again I'll say easy concept, that is bonding theories. Okay, so see you soon in the next episode. Till then, take care. Okay.